Hi everyone. Today the topic is density of states of two-dimensional structure. The two-dimensional structure is a quantum well. Quantum well or a quantum confined two-dimensional structure is an electrically isolated region. Example thin film. It is free to move along two dimensions and restricted to move in one dimension. So here consider a particle like electron which is freely moving in this two-dimensional structure. Let A is the length of the box, or we can consider that as width of the box, and Y dimension is also considered. So it is the quantum well or two-dimensional structure. The definition for density of states for quantum well or two-dimensional structure is number of available energy states per unit area in the energy interval dE, which is given by Z of E dE. Consider circle. A circle is a two-dimensional structure. Let us consider two circles as shown in the diagram. Name that as circle 1 and circle 2. The first circle is with radius n and with energy E. The second circle is with radius n plus dn and energy E plus dE. So, we are going to find the number of available energy states in this energy interval dE. Since we have considered the circle, the area of the circle of radius n plus dn is pi n plus dn the whole square, because area of the circle usually it is pi r square. Here the second circle has radius n plus dn. Area of the circle of radius n and energy E is pi n square. We have to find the number of available energy states between these two intervals. Therefore, A n plus dn minus an is equal to pi n plus dn the whole square minus pi n square. Expanding this and taking pi outside the common term, n plus dn the whole square minus n square. So it is just like a plus b the whole square. Therefore, pi into a square plus b square plus 2ab. Then minus n square. Plus n square minus n square get cancelled off. And here we are talking about electrons and their orbits. Therefore, dn is very small. Therefore, the value of dn square can be neglected. Therefore, here dn square can be neglected. So, we get pi into 2n dn. Then, the energy of the electron should be taken as a positive value. Therefore, here in a circle, we have plus x, plus y, minus y. Among these four parts, we call that as a quadrant. Therefore, among these four quadrants, only one will have this positive value, remaining will have negative value. Therefore, the energy of the electron is taken as a positive value and the positive quantum number should be considered. Therefore, among the four, only one will have the positive integer value. So, multiply this with 1 by 4. 2 and 4, we get pi by 2 n dn. So, now n, as for this explanation, it is radius, a quantum number. We need to find the expression for ndn in terms of energy, because the topic is about density of energy states. the energy of the particle is n square h square by 8m a square. So here we have n square. Therefore, n square is taken on one side and the remaining values are rearranged as 8m a square e divided by h square. Then differentiating n with respect to e, because in this formula we have dn. Therefore, 2n dn is equal to 8m a square by h square is common and e is taken as dE. Here m is considered as effective mass of the electron. When the electron is moving in a periodically changing potential, then the rest mass of the electron should be taken as effective mass of the electron and it is called as m star. Therefore, we have n dn is equal to 1 by 2 8 m star by h square a square d. Substituting the value of n dn in this equation, we get, so here we have pi n dn, pi by 2 n dn. So it is taken as density of energy states can be defined as the number of available energy states per unit area. Therefore, area should be taken as unity. Therefore, we are going to take area as unity in this expression. So, we have pi by 2 n dn divided by a. So, pi by 2 n dn is 1 by 2 8 m star by h square a square into d. Here a is considered as a square. So a square get cancelled off. Otherwise we can consider this as unity. Then also we have, according to Pauli's exclusion principle, each energy state, energy level can be occupied with 2 electrons with spin up and spin down. Therefore, multiplying the above equation with 2, we get 2 into pi by 4 8 m star by h square into d. So we have z of e dE as pi by 2 8 m star by h square into d. If we consider this as unit energy or the energy interval, these two can also be taken off. So we have pi by 2 8 m star d in this energy interval. Even we can cancel these two if it is unit energy. Now h is called as Planck's constant and we have this h cross as reduced Planck's constant. Reduced Planck's constant is equal to h by 2 pi. Here we have h square. Therefore, h is equal to 2 pi h cross. Therefore, h square is equal to 4 pi square h cross square. Now, substituting h square as 4 pi square h cross square, we get 4 into 2, 8 and 8 and pi get cancelled off. We get m star divided by pi h cross square and this dE, the energy interval, can be taken as E minus En and it is a summation value. that is sigma is considered here. We are going to find what is En, that is if there are n number of energy states available in this two-dimensional structure, then n is that maximum energy state and E should be the lower energy state, but it should be greater than or equal to E naught. And sigma denotes it is a step function, that is just like, let us consider along the x-axis the energy of the electron in this two-dimensional structure is taken, and along the y-axis the density of states of the two-dimensional structure is taken. The electron will be moving as x, y, x, y, x, y in this way, which means that it is moving in two dimension. The sigma denotes it is a step function. For the energies E greater than E naught, greater than or equal to E naught, the two-dimensional density of states is a constant and it does not depend on energy. That is why Z of E or density of states of 2D is equal to m star pi h cross square summation of sigma E minus En. Here En denotes the energies of the quantized state and sigma E minus En denotes it is a step function. So here we have derived the density of states of the two-dimensional structure.